Hello everyone, in this video we will be talking about the Kibble Balance, the instrument that redefined the kilogram. It changed the whole definition of the kilogram, what it was back then, and now the definition of the kilogram is changed. So the first thing you'll be noticing will be that I switched from OneNote to the PowerPoint because of some inconvenience here because of some reasons because I just my drawing tablet is not with me right now, so I just can't draw equations or write something on the screen, so it's a little inconvenient. So sorry for the inconvenience. um, so I just made a PowerPoint presentation. I know most of the people don't like a presentation. It's like boring, but I'm really sorry about it because I really wanted to explain it by drawing equation and drawing the diagrams. But right now I don't have that the drawing tablet with me, so I'm really sorry for the inconvenience. So let's get started. I hope you will enjoy this video as much as my previous as much as the previous ones. So let's get started with the Kibble balance. First of all, we're gonna talk about the kilo of the previous definition of the kilogram here right here. So in the recent video I talked about in detail the history and the definition, old definition, and then the new definition of the kilogram, everything about it. So make sure to watch that video first and then come to this video. We're gonna in the previous video we stopped at the new definition of the kilogram. The new definition of the kilogram is kind of not so it's really difficult, not can be cannot be explained in cannot be explained easily. So it can be only be explained when we try to explain how it was made by the help of the Kibble balance. So first of all, very short introduction to the kilogram. So what was kilogram? Kilogram was actually in the past was just a hunk of platinum iridium metal that was kept by the International Bureau of Weights and Measures. So that was just the definition of the kilogram. Of all the seven base units, only the kilogram was the only SI base unit that was defined based on a physical artifact. So the problem arose when they tried to create copies of the kilogram and send them all over the world. So they kept track of the mass of those replicas too, and the original kilogram. But soon, after a few decades, they found out that there is some difference in mass in comparison to the kilogram and all the other replicas of the kilogram. So what was the difference? The difference was about, sorry if I take a little time here. So I'm using mouse, so I'm really sorry I don't have the drawing tablet with me. So here, oh, let me just, okay, that was odd. So the difference was 50 microgram. So 50 microgram is kind of like the mass of your eyelashes, something like that. A really tiny difference here, but but there was but that difference was too much, because when you are talking about the absolute unit, that a unit that can be explained that does not change over time, that stays the same. 50 micrograms becomes a very big value for them, especially when you are trying to measure tiny measurements. When you are measuring something very tiny on a small scale, 50 micrograms becomes a whole lot. So they so they then try to redefine the kilogram in terms of one constant, the one natural constant of the universe. Like there are many constants of the universe, like gravitational constants, etc. So here the constant we are using is known as the Planck constant, which value is about 6.62607015 multiplied by 10 power minus 24 joule second, which is equal to kilogram meter squared per second. So they tried to redefine the kilogram based on the Planck's constant. So what was the definition? What is the definition now for the kilogram? Now is the definition is as written here. Uh, The kilogram, symbol kg, is the SI unit of mass. It is defined by taking the fixed numerical value of the Planck constant h to be 6.62607015 multiplied by 10 power minus 24 when expressed in the unit joule second, which is equal to kilogram meter squared per second, where the meter and the second are defined in terms of C and delta VCS. So here, first of all, I will try to clear this when expressed in the unit joule second. So when expressed in the unit joule second, when you break joule second, also break joule second down. So the basic units become kilogram meter square per second here. Okay, now now again, and then it says where the meter and the second are defined in terms of C and delta VCS. So here it's saying that that the meter and second you are seeing in the unit are defined, are measured in terms of the natural constant that we defined for them. Like for meter, if we know it was also a artifact, and then it was attached to the constant speed of light. So meter is now defined in terms of the speed of light. Here it's saying the C. Okay, and then it says delta VCS. So what is delta VCS? It's for the second. So now the new modern definition of a second is that the cesium atom takes about I believe approximately 9 billion vibrations. So that becomes 1 second. So here delta VCS is the now redefined definition for the second, and meter is according to the speed of light. So here we're kind of done. So let's go to the upper section. From the start, the kilogram here. It is defined by taking the fixed numerical value of the Planck's constant h to be this when expressed in the unit joule second. So basically it's saying that, okay, we have a kilogram. Okay, we're just gonna attach it to the Planck's constant. We're gonna have a universal constant of the universe, and we're gonna attach it to the kilogram. So I know it doesn't make any sense, but when I'll go through the Kibble Balance, you'll see how these things just matches up really greatly. So let's go to the Kibble Balance, the instrument that was used to redefine the kilogram. So here we're gonna talk about a short intro here. So here you're saying watt balance. I'm saying about Kibble Balance. So before the Kibble Balance, it was known as the watt balance. So watt balance was invented by Brian Kibble in 1975. So the reason why was it called watt balance was the because the weight of the test mass is proportional to the product of current and voltage, which is measured in watts. So it's basically telling you, in the old days when you had a weight beam, a beam balance, where you had put we put stones in one pot, and the and some stuff like vegetables or something, fruits, on the other pot. So we weigh down. So what is helping us to measure this? Obviously gravity is helping us, right? So in this case, gravity, we just cancel out the gravity. We will say no, no, we're not gonna take the help of gravity. Instead, what we're gonna use is the current and voltage. So the product of current and voltage counteracts the weight of that of the other product. So which is measured in watts. That's why it's called the watt balance. So why was it changed to the Kibble balance? Here we have the third point about it. Why was it changed? Renamed to Kibble balance in the honor of its inventor 2 months after its death. So it was invented by Brian Kibble in 1975, but after his death, the other invention, other scientists thought so it will be great to have to rename the watt balance to Kibble balance in the honor of its inventor, Brian Kibble. So that's why it was changed from watt balance to the Kibble balance. So what basically, so we're gonna go through the definition. Here I have shown, I have explained a little by the definition. So we're gonna explain it a little more. So here is the picture of the Kibble balance. Wow, just it really is something. When you talk about these, it's a definition, it looks like a simple definition, but when you see the whole instrument thing, it looks like it just blows your mind. So how much engineering, how much work was applied to make this beautiful thing. So according to the definition on the Wikipedia here. So it says Kibble balance. A Kibble balance is an electromechanical measuring instrument that measures the weight of a test object very precisely by the electric current and voltage needed to produce a compensating force. It is a metrological instrument that can realize the definition of the kilogram unit of mass based on fundamental constant. So basically what I told you about here, what I said here, it also applies here. So it says that it's electromechanical measuring instrument that measures the weight of a test object by the help of what? By the help of electromagnetism, by the help of electric current and voltage that is needed to produce a compensating force. So here compensating means the opposite and equal force to counteract that weight. It is a metrological instrument. So here it's a metrological. Metrological means dealing with the metric stuff, like the main units we are talking about. So it's the metrological instrument that can realize the definition of the kilogram unit of mass based on fundamental constant. So here we know the fundamental constant is the Planck's constant. So we're gonna talk about now the working of Kibble balance. How in the world does this thing works? So in the next slide we have will just show we'll just talk about short explain it to you about the structure of the Kibble balance. So there are on two modes of working for the Kibble balance: force weighing mode and then velocity mode. So here I have the diagram here. um, so let's first talk about here this section here. So instead of putting mass to the opposite side, we test mass here. So here we put the kilogram, the object, and then weigh it down. So here with below we have lasers. So this is called the interferometer. The interferometer is a very accurate measuring device for measuring discrete speeds. So what it is trying to measure is the length, is the speed, is the velocity of the coil that moves. So here we have coil, and the red thing here is magnet. So you know that when current passes through a coil, it creates a magnet we call an electromagnet. So here basically it's doing the same. So I'm not gonna go into detail because in the next slide I will go into detail. So the same is here also. So I think we're gonna go to the next slide and explain it and explain the force weighing mode. So how do we measure the kilogram? So in the first mode, force or weighing mode, we have, as you can see, object kilogram has placed there. So here in the force or weighing mode, the mass of the kilogram IPK, the IPK means international prototype of kilogram, is balanced by inducing current in the coil that is sandwiched between two magnets. This creates an electromagnetic force known as the Lorentz force that counteracts the weight of the kilogram. So here we have the mass, and then we pass the current into the coil. So what does current what becomes of the coil when current is passed through it? It becomes an electromagnet. So the electromagnet, the force that is created then inside this inside this container, which is the coil sandwich between the magnet, it creates a force, electromagnetic force known as the Lorentz force. So what does that force do? The force just counteracts the weight that is above. So how does it do? I mean, the weight isn't it in the opposite side, so it makes the whole system in equilibrium. So that's how we'll find out that it's counteracting precisely. So the interferometer is also about locating where the coil is, about how much it is, and how much it is, also to calculate its velocity. Why velocity? Because here we don't have any v. So why velocity? In the next mode we're going to talk about the weighing, the velocity mode. But here, so the electromagnetic force counteracts the mass of the kilogram. So what is doing what is the weight of the mass, right? The force, what is the force that's pulling the mass? It's the gravitational force, right? And here we have, so the gravitational force equal to the electromagnetic force, which is the Lorentz force. So it is so what will be the equation? It's the mg, mass of that kilogram, g is the gravity of the earth, equal to bli. So here b is the magnetic field, and the length L is the length of the coil, and I is the current that was applied to the current, to the coil in order to for it to become an electromagnet. So here we can say, like, all right, everything's done. We got all, we got the equation. We know the mass, we know the gravity, we know the gravity of the earth equals, we know the we can measure the magnetic field, length of the coil, and current. Everything's done, right? Perfect. We're gonna redefine the kilogram. So not so we just can't, because number one, of course, when we are trying to measure something, we need to be accurate as possible, and there are two corporates here who can, which cannot be measured very accurately with respect to the other three units, three units. So who are the two culprits here? We have the magnetic field, and L, we have the length of the coil. So these two things cannot be measured accurately. So we need to then get rid of magnetic field and length of the coil by introducing another equation, so that BL can be cancelled, and so we can go around this situation in order to introduce a new variables in order to redefine the kilogram. Also we need to put the Planck's constant in it. So here, that's why the second mode comes into place. So what is the second mode? We have the velocity mode. Now here, when you see the structure of the Kibble balance here, you will see that the mass of the kilogram has been removed, because now, in this area over here, the inside of the coil will be moving at a constant velocity. We will try to move it in a constant velocity inside these magnets. So what will this do? This will introduce a voltage. This will introduce voltage into the coil, into the other side of this container. So what will be? It's like, first of all, let me just let me just say it. The second mode is the velocity mode. In this mode, the motor on the other side moves back and forth in the magnets at a constant velocity and generates a voltage into the coil of the other side. That is given by the equation V equal to BLV. So here the coil moves at a constant velocity, a velocity that doesn't change it, obviously constant velocity, and then that produces a voltage. So the equation is given by voltage equal to BLP. So here B is the obviously magnetic field, just magnetic field. L is the length of the coil, and V is the constant velocity. So we need to have a constant velocity that doesn't change. Obviously, if we have a velocity that changes, it will hinder in our results also. So here we have V equal to BLV. So here we have BL, and in the previous equation we also have BL. So we're gonna cancel it down, and in the other side we have mg by I, which is going to equal to BL equal to V by small v. So here obviously V is gone to the other side, divided by V it becomes, and also I goes to the other side of mg. So here B is then cancelled out, and then we have mg by I equal to V by small v. We then have, here we're gonna do the cross multiplication, and we have then the product, the final, obviously final equation. We have the mgv equal to Vi. So here mgv is the mechanical power, also expressed in watts, equal to Vi, which is the electrical power, also measured in watts. So here now becomes, and now we know the values of m, g, and v, but we need to find out the we need to accurately measure the voltage and the current now. So how will we measure the voltage and the current here? So there are two topics we will introduce here, because these are the two topics, these are the two things that are used in order to accurately measure the voltage here. The reason I didn't said current, because we're gonna remove current, because the method of measuring voltage is so accurate that we simply do something like, V equal to, sorry about the writing, V equal to IR, right? So what we're gonna do, I becomes V by R. So this will become V by R. So instead of measuring current, we're gonna measure the resistance. So how we're gonna measure the resistance? We're gonna go through the topic, but first we're gonna talk about the voltage here. So how voltage was measured accurately? Here we have the Josephson's junction. This is the thing that made us to calculate the voltage so accurately, that we didn't that we remove the current, and instead we are now measuring the resistance. So voltage is accurately measured by Josephson's junction. So what is Josephson's junction? So so here it says Brian Josephson predicted in 1962 that pairs of superconducting electrons could tunnel right through the non-superconducting barrier from one superconductor to another. He also predicted the exact form of current and voltage relations for the junction. So the junction is known as the Josephson junction, obviously because of Brian Josephson, who predicted in 1962, and he predicted so precisely with his equation as given here that he was noble that after doing experiments he was concluded right with this with the equation that he derived here. So the experimental evidence proved that he was correct, and due to this he was awarded Nobel Prize in 1973. So what is Josephson junction? So Josephson's junction is uh, that a tiny layer of a tiny insulator is sandwiched between two superconductors. So when you throw the microwave microwave frequency, a certain radiation of certain frequency, the electrons just tunnel through the insulator, and it produces a voltage. So that's why I'm here a voltage meter. So it introduces a voltage when you introduce a microwave frequency, a radiation of any frequency, of course. So what was the voltage equation? So here is the hence the Josephson junction provides a stable and accurately measurable voltage which is situated inside the coil. Uh, the equation is given by V equal to NHF by 2E, which is situated inside the coil, meaning the coil that is used in the Kibble balance. Here we have V equal to NHF by 2E. Here N is the number of junctions. So here we have one junction. We can stack up to many junctions as possible to produce a higher voltage. H is the Planck's constant. F is the frequency of the radiation. 2E. Is the charge of an electron. So from this we can very accurately measure the voltage through the Josephson junction. So then we have our resistance. So how will we measure the resistance? Is through Hall effect, or when you go more quote unquote quantum, you call it quantum Hall effect. So what is quantum Hall effect? Well, the quantum Hall first we're going to talk about the Hall effect, and then we're going to talk about what is quantum Hall effect. It's not a big difference, just a small difference. The Hall effect is the voltage difference in a sheet of metal which has a current going through it when a magnetic field is applied perpendicular to the current. The magnetic force carries the positive charges to one side and negative charges to the other, hence creating a voltage difference in the metal sheet. The magnetic force is perpendicular to both the current and the magnetic field. The Hall resistance is created due to the immense voltage in the sheet. Since we are dealing with the quantum Hall effect, the voltage is then quantized. Therefore, its equation is given by R equal to 1 by P H by E squared. So, what it is exactly saying? So, first we're going to talk about the Hall effect. So, what is Hall effect? Hall effect says when you have a sheet of a conductor, right? You pass current through it. So here we have the battery, here is the direction of the current. So when you pass current in it, so when the current is flowing through the conductor, you introduce a magnetic field. So here we have the magnetic field which is perpendicular to the current. So what does this magnetic field do? It splits the electrons and the protons to one side of one side of the conductor. So here we will have the electrons in one side and the protons on the other side. So this creates a Hall effect. So it induces a voltage difference here, because obviously we have electrons here, protons here, plus charges, negative charges here, positive charges here. So it creates a voltage difference. So it's called the Hall effect. So what is quantum Hall effect? Quantum Hall effect is just like the Hall effect, but things get on a quantum scale. So in quantum scale, we talk we take the a sheet of a conductor, but instead the sheet of the conductor, its width is so tiny that its thickness is only a few atoms thick. It's like literally the 2D shape, 2D sheet of a conductor. So we take a very small thickness, a very a very tiny scale thickness of a conductor sheet, and then we scale up the magnetic field. We make the magnetic field more strong. So this is the quantum Hall effect. The effects are the same. It introduces the voltage difference here. As you can see, the negative charges are here now, positive charges are here now. So what the magnetic force will do, as you can see, the positive charge, it will move the positive and negative charge to the other side of the conductor. So it says the magnetic force is perpendicular to both the current and the magnetic field. So here current is moving, we apply magnetic force, so magnetic field, sorry, we applied magnetic field. So magnetic field is perpendicular to the current, but the magnetic force is perpendicular to both the current and the magnetic field. Okay, so the Hall resistance is created because when you are talking about the quantum Hall effect, the voltage is quantized then. So therefore we can measure the resistance, that is the Hall resistance, very accurately. That is given by the equation R equal to 1 by P by 1 by P h by E squared. So here is P or rho, some call it. So here this P or rho, you can say, is the resistivity of the conductor. So it's the natural resistivity of the conducting material. So with the Josephson's junction and with the help of quantum Hall effect, we can accurately measure V voltage and resistance also. So in the end, we take V and then we take our resistance. We take these values and combine it to define an equation that we had here, and then we have mgv equal to v squared by r, and then putting the value of v and r, we get mgv equal to rho n squared f squared h by 4, and hence we have h equal to 4 by rho n squared gv by f squared m. So we're gonna talk about you all will be asking about did you derived h uh, why did you derive the h? You can simply end it with the mass here. So h is very the definition I talked about in the very beginning of the video. Let's go through it. It says taking the fixed numerical value of the Planck's constant to h to be 6.62607015 multiplied by 10 to the power minus 34 joule second. So this whole value is fixed. If this value wasn't fixed, we cannot accurately measure the kilogram. So when we put all the measuring values, numerical values in, the h has to be 6.62607015 multiplied by 10 to the power minus 24 j/s joule second. Here m, we're gonna simply take m as 1, because obviously 1 kilogram, this is the 1 kilogram we're talking about, the international prototype of the kilogram. So h will be that the fixed numerical value 6.62607015 multiplied by 10 to the power minus 34 joule second. And then as the value of h is fixed, therefore m equal to pn squared by 4 f squared by gvh. So we're gonna take the fixed value here, and then we're gonna have m equal to 1 kilogram. So this is whole point of saying is that this is the equation. We're gonna first deduce the value, the numerical value of the h, which is fixed by that specific number, and then putting that number in m, we get 1 kilogram. So they are really correlated to each other. The reason why we fixed the Planck's constant was the reason because we wanted to have a non-changing the non-changing mass of a kilogram. So that's why we wanted to fix the h. First we derived the equations for h, and then h by making h a fixed value, we then introduced it to the mass equation, and then we get mass equal to 1 kilogram. So that's it. I hope you have liked this video, and if you have, please like and subscribe to my channel for more future videos. And I'm sorry if I forget something, or did or given you any misinformation. I'll check it again. So yeah, let's in the next video we will talk about the other remaining SI base units. And I hope you have enjoyed this video, and please subscribe to my channel, and I will see you in the next video. Thank you for watching.